would you do if you're a poltergeist?
Differential calculus in a nutshell. So, we have a function. It's not very dark at all. Alright, there's its graph. And we want to get an idea of how fast the function is changing. Thank you. At this point. Okay, so a rate of change is generally, mathematically, the slope of something measures its rate of change. But we only have a well-defined notion of slope for what kind of objects?
Straight lines.
Straight lines, right. We have a nice formula, change in y over change in x represents the slope of a line. Well, this isn't linear. It's got some curve to it. But what we could do is we could approximate it with lines. So, I could draw a line that connects this point to a point over here. Like that. I don't know why it's writing so faintly.
Maybe it's like the brush size or something.
It's really bright.
Huh.
I'm
It's
using...
at 5.5.
Is that what I'm using?
Can you have a function like that that gets thicker?
No. The thickness of a function is, I mean, functions, I guess because points don't have any thickness, functions don't actually have any thickness either.
So you could, that'd
Yeah.
be really cool.
Well, I suppose maybe in 3 dimensions you could have such a thing.
That'd be awesome. When do we get to
Okay, that doesn't seem to be
play
writing
with
at all.
three-dimensional functions? What math do I have to be in to do that?
Multivariable calculus.
Filtip marker. Filtip marker.
Where is that? Oh,
Because it looks cool.
okay, that's really fat.
Woohoo!
Yeah, that's a little extreme there.
You change the brush size.
Yeah, let's do that. Like a lot. Not that much. Okay, so let's try that again. That's much better though.
Yeah!
Alright, so now I need a new color. So I choose a point that I want to know how fast the slope is changing. Okay, but I can only do that with a line. So I might choose a point near it.
Oh, and then you look at the slope of the
And
tangent
I look
line.
at, yes, so
And you look
this
at
line
slope
right here
of
is not a
calculus.
tangent line. This is called I kind of love this color, secant line.
It's really pretty.
Okay, and so what I did is this point right here, we'll call that x. We'll call this over here, value over here, this is f of x. I changed x by a little bit. I added some small quantity to it, which we will call delta x. So then this becomes, up here, this is f of x plus delta x, right? So now I have 2 points on my line. I have the line x f of x, I mean the point, not the line, and then I have this new point, x plus a little bit, f of x plus a little bit, right? Those 2 points define my secant line. All right, what is the slope of said line?
It's going to be f
delta
of,
x over x.
no, it's going to be f of delta x, f of x plus delta x, minus f of x plus, over x plus delta x minus x.
Perfect. Right, that just comes from the straightforward geometry definition of the slope of a line. Change in y over change in x. What happens to the bottom of this thing if I do algebra onto it?
It goes
Cross out
to
the
delta
x's.
x on the
Yeah.
bottom.
Alright, so this quantity that I've written right here, whoops, represents the slope of a secant line. So a secant line is just a line that connects 2 points that sit on your graph. And it has a well-defined slope. Okay, to get the tangent line, what do you think we do? Since it's calculus, and calculus is not just simply about algebra and geometry, which we've done so far. Calculus is about,
Rate of change.
yes, in particular, I mean, every single thing in calculus that you do comes down to a limit. It all comes down to a limit. We will be evaluating limits as something goes to 0 in differential calculus, and we will be evaluating, well, you can either think of it as limits as widths go to 0 or limits as quantities go to infinity when we get to integral calculus. So, okay, so to find this tangent line, we take smaller, smallier, and smaller delta x's. So,
Took me way too long to see where you misspelled something.
here's my curve. We're going Christmas now. Alright, so that might be this might be x plus delta x1. Alright, that gives us a secant line. Now imagine shifting that over a little bit. This is now x plus delta x2. You can see that the first line, the first secant line looks like that one. The second secant line looks like that one. That's a really
It
weird
mixes
color.
with the green, because it's
Makes
a
up-
felt
Oh,
amount.
how strange. Okay.
It's kind of
Then I could
cool.
do a point here. We'll call that x plus delta x3. And we have this line that I can't draw because I haven't mastered this tablet yet. Looks like that, but you can see that as the delta x's move closer and closer to x itself, we get something that's closer and closer to what we might consider this tangent line, which is going to be a line that just touches that curve in that one point. It might intersect it somewhere far away, but near it, it only intersects it in that one little point. Okay, so by making delta x smaller, in calculus terms, what am I doing?
Approaching the value of x.
Close. Delta x is actually approaching what here? Yes, it's going, because it's the
Oh,
quantity that I'm
yes.
adding
It's
to
getting
x to move
closer.
away from it, it's going to 0. So what do I put up here to make this look like calculus? When I say that delta x is going to 0, I am taking
approaches 0.
this.
Delta x.
The limit as delta x approaches 0 of the slope of each of those secant lines, which look like this. So, this is a well-defined quantity that we get by taking our original point where we want to know the slope, some point close to it but not exactly next to it, and calculate the slope of the line that connects them. We make that distance smaller and smaller and smaller and smaller when we get, obviously not quite to 0, because then we would be dividing by 0, but as small as we can get, as small as we want to get, we then define that to be the slope of
Or
the tangent line,
Yay.
which in calculus is another name for the derivative.
Yay!
Woohoo.
We know how to do derivatives.
You now know everything that essentially you need to know about derivatives. This right here is the thing about a derivative that you must remember, that it represents the slope of the tangent line. So if I say to you, what is the derivative of x squared? And you tell me it's 2x, I'm going to tell you you're wrong. 2x, we're going to find out very shortly, represents a formula for the derivative of x squared. The derivative of x squared is the function that we'll see in a little while that we can get actual functions out of these rather than just specific values. It is a new function that defines the slope of any tangent line that we want along that curve. And most of the formulas that we work with have very nice formulas for their derivatives, but I don't want you to start confusing the derivative, the formula for the derivative of a function with what the derivative actually is, which is this thing right here. It is always the slope of a tangent line. Alright, so